So on Tuesday, we talked a lot about where Earth's energy comes from, the fact that 99.99% of our energy, everything, that energy that fuels life on Earth, that fuels the movement of air and of water, that fuels our climate system, comes from the sun. And we talked about the different ways that energy can come from the sun, in particular that electromagnetic radiation, and it travels as these waves through space, and the wavelength is how we define different sort of types of electromagnetic radiation, everything from visible light, what we use to see, through to infrared, through to radio waves. All of these are types of electromagnetic radiation. And then we talked about what patterns through time affect, say, or cause our day and night, and the fact that we have seasons on Earth. Today we're going to sort of take almost a little bit of a step back again, and we're just going to look at what factors really go into controlling our global temperature. What set of factors have somewhat miraculously combined to create a temperature that means that life on Earth can exist and can exist very comfortably and successfully? What factors have really changed through time that have allowed that to happen? And so what we're going to do today is sort of think much more in detail about those. So first of all, because I keep forgetting to say it, thank you so much to those of you who sent me your introductions. I really enjoyed reading them, and I think I have a better sense of who some of you in the class are. So thank you for doing that. That really helps me out. Other quick reminders. If I'm scaring you off completely, then tomorrow is the last day to drop. So hopefully you're finding it interesting so far, but please make note of that date. Quiz 2 will be available from 4 p.m. today, so once I get back to my office and start it, basically, until 11 a.m. on Tuesday as usual. Okay, so remember that you have 3 chances to have a go at Quiz 2, and I just take your top score, so you have nothing to lose by trying a second or a third time, but please don't do it more than that, because it's sort of for academic honesty as much as anything else. So this is what I was saying. We had found that we had this solar constant that's created by the amount of energy being put out from the sun and our distance from the sun. But we have day and night due to rotation around this axis that runs between the North Pole and the South Pole. And we also said that we get seasons because that axis isn't perfectly up-down in space. It's tilted over ever so slightly. Without that tilt, we wouldn't have the seasons that we have today. And that's because we affect the length of our day. In our summers, we have nice long days. That means we get more energy over that same sort of time, and so we are warmer. That energy is also being less spread out because it's coming more straight down rather than from the sides, and so we're just heating a smaller area with that same energy. And then lastly, it's just traveling through less atmosphere. And that part today, talking about how that atmosphere interacts with everything else, that's what we're going to focus on. But, do you remember I made you a deal? Hopefully you had a chance to look at this. I decided to take pity on you a little bit, and I've rewritten I haven't rewritten the question, but I've given you 2 diagrams that should help you out. So at the top there, you can see the tilt of the Earth at aphelion, which is the point where we're furthest away, which is July 4th today, and perihelion in January 4th, which is when the Earth is closest in its elliptical orbit to the Sun. Below that, I have what would happen if that was reversed. So what would happen instead of having our winters on January the 4th at perihelion, where we're closest to the Sun, what would happen to our winters if we instead have our winters when we're furthest away from the Sun? And then think about what would happen to our summers. Where do we have our summers today in that elliptical orbit? Where would that be if that was reversed? Okay? So think about it for a couple of minutes. You should have done this over the last 2 days. Let's see if we can get better than a 50-50 this time around. So I'll take that. That's good enough for me. It's a tough question, I do realize that. So we have a 60-40 split, okay? So right now, if we think about it, we're in the top, for the 40% that didn't get it, we're in the top diagram. So today, in January the 4th, the northern hemisphere is tilted away from the sun, so we're in winter, January the 4th, that makes sense. but we're closest to the sun in our elliptical orbit. If we go to the bottom diagram, if we instead had winter when we're even further away from the sun, what's that going to do to our winter temperatures? It's going to be colder. If we go from having winter when we're closest to winter when we're furthest away, our winters are going to get colder. If we look at what's happening with summer, you can see in my top diagram, on July 4th, that northern hemisphere is pointing towards the sun, and it's at the furthest away point on our elliptical orbit. So what would happen if we then switched, and instead we had summer at perihelion when we're closest to the sun? So we've gone from having summer furthest away to summer closest. What will happen to our summer temperatures? They'll get warmer. Does that make more sense now for those 40%? Yes? Okay. It takes a bit of thinking about, but this is why I say drawing diagrams is really the only way of doing this sometimes. So please do always sort of draw out diagrams. It really does help you think about these things. So you'll have a chance to practice this again in the quiz. Okay. So if we think about all of those things adding together, if we take a look at what that incoming solar radiation is, which we sort of shorten to call insolation, incoming solar radiation, what it means is that if you see where that red band is, that's where the most radiation is occurring. And you can see that it moves north and south over the year, basically with the seasons. And when it's, say, in the southern hemisphere right now, it's summer. Okay? And you can see that in that summer hemisphere, whether it's north or south, when it's summer, there isn't really much of a difference between the pole and the equator. And that's quite important because that difference in temperature between the pole and the equator is what drives a lot of our weather. It drives a lot of the movement of the atmosphere and the oceans. Whereas you can see that in the winter hemisphere, so where the little blue comes up, you can see that there's a really big difference in the winter between what's reaching the pole and what's reaching the equator. And again, that's really important because it's that difference between the pole and the equator that drives that movement of air and of the oceans. Okay? So that's what happens when we take all of those things into account. So what are we going to do today? We are going to think about Earth and the Goldilocks zone. And so hopefully everybody has heard of the three bears. And so one was too tall, one was too short, one was just right. So Earth is very much like this. So if we look at the planets nearest us, which one is this planet on the left? Venus. Which is the one on the right? Mars. We are in the Goldilocks zone for life and for water to exist. On Venus, it's slightly closer to the sun. We don't seem to see much life. On Mars right now, it's further away from the sun. There might arguably have been life in the past, but certainly it's very difficult for us to track it down today, even though we're not giving up quite yet. And so what we're going to talk about today is understand the different factors that have resulted in our planetary, what we call energy balance, and what sort of sets our global temperature. And then to really sort of start thinking more interactively about this, we're going to have a look at two particular examples. We're going to see how these factors have altered over Earth's history to create this amazingly stable temperature, which has allowed complex life to evolve and exist and civilizations to develop and intelligent life to exist. And then we're also going to take a look at using those different factors that we talk about to see if we can predict something about the temperatures that we might see if we were to stand on Venus today and if we were to stand on Mars. And that's what your little bit of paper is about, and we'll go through that at the end. So that's what we hope to achieve today. So our first factor, which is basically a repeat of Tuesday, is the solar luminosity. So I just gave you a value for the solar luminosity, which is at 3.865 times 10 to the 26 watts. And I said, that's our solar luminosity. And that is absolutely our solar luminosity today. But actually, over billions and billions of years, the sun has been getting brighter, which seems completely counterintuitive, right? Because you think, well, usually things get dimmer through time. The sun has been getting brighter. It's been giving out more and more energy through time. Okay? And eventually, it's going to swell up and sort of swallow the Earth. But anyway, not on our time scales. And so we have these really long changes in solar luminosity. We also have much shorter time scales. Who's heard of sunspots? Is that something that a few people have heard of sunspots? These are little dark areas that you can see on the sun. Don't stare at the sun, but when they're there, if you use the right telescope and everything else, you can see these little dark areas. And again, counterintuitively, it actually means that the sun is brighter during that time. There's more activity going on at the sun. Okay? And what we can see is that there's an 11-year, what we call a sunspot cycle. We go from having lots of sunspots to very few to lots to very few on this 11-year cycle. Okay? And so you can see that we have this amazing record going back almost to the 1600s, thanks to some old dudes in Europe that seemed to have nothing better to do than count sunspots. But it was very helpful. They were discovering the world, and they left us with this amazing record. Because not only do we see that there's this 11-year cycle, but you can also see that through time, we see variations on, say, maybe hundreds or longer timescales when the sun's activity is much more or much less. And we don't necessarily completely understand why we see this longer-term variation. We don't have that great records of the sun sort of outside of what we have satellite measurements of. And so this is something that we'd love to understand more about. And the physics of the sun is really, in some ways, a little bit more of a mystery than we would like. But the changes that we see in the sun on that 11-year cycle are really, really very small. They're really very small. And so they do have a tiny influence on climate, but it's certainly not that substantial. So the second thing that controls our planetary temperature is the distance from the sun. And this is one thing that you can be pretty certain isn't changing through time. Okay? So our distance from the sun isn't dramatically altering. Okay? And these were the two things that we used on Tuesday to create our solar constant. So if we looked at the solar constant in the past, when solar luminosity was lower, we'd have had a different number. Today, it's that number we calculated. So now we want to think about, well, that's what happens to the energy that's arriving at Earth. But what really happens to that energy once it hits Earth, once it hits the atmosphere, once it has to travel through? So we're going to talk about that now, and we're going to introduce this strange word, which is albedo. So anyone that's taken a class with me before has probably heard of this word and is familiar, and you will all be very familiar with this by the end of the course as well. So this funny word, albedo. So as a reminder, on Tuesday we said that if we put a satellite above Earth's atmosphere, then this is the sort of spectrum coming from the sun that we might observe. And the peak of that spectrum is in those visible wavelengths, but it also produces some ultraviolet, some of those shorter wavelengths, and some infrared, some of those longer wavelengths. So what happens if we instead measure that down here at sea level? So now you can see that orange line is what we'd measure outside the atmosphere, and that colored in area is what we would actually measure down here. And you can see that something is going on. In fact, a whole bunch of stuff is going on. First of all, we're just getting less down here at sea level. And some of that, and also, for example, in the infrared, we see these giant holes in that spectrum where whatever was coming in at that particular wavelength isn't coming in anymore. Something's happening to it as it goes through the atmosphere. So we're going to talk about why we see these differences. So first of all, what we do get down here at sea level is what we call transmitted. It's traveling straight through the atmosphere. It's not being reflected or absorbed or anything else. It's coming straight through. It's being transmitted. Okay? So what we measure down here is what's coming through. But we also have a certain amount that is being reflected back and that is being scattered. So everyone is familiar with the concept of reflection because we all have mirrors. Okay? Even if you're not that vain, you probably have a mirror of some sort hanging around. And so what happens there is that radiation comes in and is redirected in a different direction. And with a nice, sort of good mirror, then that happens very cleanly, and all of that light is reflected away and redirected. And we call that specular reflection. That's what's happening in your mirror. But in the atmosphere, we also have other things going on. We have something called Rayleigh scattering. And this is where that incoming radiation, that incoming electromagnetic radiation, hits the different gas molecules in our atmosphere. And instead of just bouncing off in one direction, that energy is scattered in all directions. It continues traveling, but it goes in all directions instead of in a straight line. Okay? And it's stronger for shorter wavelengths. So as a quick reminder, if we perhaps look at that visible radiation, which is mostly what's coming from the sun, if we go to the shortest end of that, the shortest wavelengths in terms of visible radiation, we get down into these sort of blue colors. Okay. And so blue is a color that we associate with the sky, and this is because of Rayleigh scattering. We are explaining now why the sky is blue. Okay? Because it is a mystery, right? If you shine a torch, then what you see is the beam of light. And so theoretically, if we're getting all of our light from the sun, we should be seeing this big giant spotlight, right, coming down. Whereas actually, we can look in a completely different direction from the one that the sun is in, and we see blue light traveling towards us. That's what gives the sky its blue color. We're seeing blue light coming from all directions. Okay? And that's because of this Rayleigh scattering. That's because as energy from the sun comes and hits Earth's atmosphere, then those blue wavelengths are being scattered in all directions by those molecules in Earth's atmosphere. Isn't that neat? No one seems that excited. Everyone's favorite question, right, when you're 2, why is the sky blue? Is it not everyone's favorite question anymore? So this is sort of what happens. This is why we see blue light. If you go outside today, even if it's a little bit cloudy, if you go out and you look in a different direction, you see blue light. It's originally coming from the sun, but then it's bouncing back at you off molecules in the Earth's atmosphere. And this is also why we see lovely red sunsets. Because if we're scattering, if you imagine that you're sort of sat there on your deck chair, this is an enormous sky. I'm not quite sure why he's half the size of the Earth. But you can see that in the middle of the day, do you remember we said that that energy traveled straight down? It didn't travel through that much of a thickness of the atmosphere. But if we think about what's happening in the evening, then we see that light has to travel a really long way through extra amounts of atmosphere. And as it does that, it's bumping into more and more gas molecules. More and more of that blue light is being scattered away. And if we're scattering away more and more blue light, what are we left with? We're left with yellows and reds. They're the longest wavelengths. And so that's why you see lovely sunsets like this if you go to Newport Beach. Okay? You can see that we still see blue light from higher up in the sky, but down where the sun's energy is coming right along the horizon through a really thick sort of amount of atmosphere, all of that blue light is being scattered away. Instead, the only thing that's left by the time that energy reaches us are those orange and red wavelengths. So isn't that cool? So the third thing that happens is something called me scattering. And this is just forward scattering. So it's sometimes, some of it comes backwards, but most of it continues in sort of broadly in a forward direction. Okay, a little bit might go back. Most of it continues in forward direction. And this is done by much larger things in the atmosphere. So not by really tiny molecules. This is now big particles or sort of little droplets in the clouds, something like that. Okay? And this doesn't care what wavelength it is. So it's not preferentially scattering the blue wavelengths. It's scattering whatever hits it. And this is the reason why our polluted areas around here give us even nicer sunsets than really nice sort of pure areas. So over the sea, this is what you might see. If you look out from Joshua Tree, you see this sort of thing instead. The air pollution, the particles in our atmosphere are taking that red light that's coming right along the horizon, and they're bouncing it around, and so we see a much thicker area of red near the horizon when we have pretty nasty sunsets. And this is something that if you look back at some of the paintings from sort of 1800s, sort of late 1700s, I think, I'm not very cultured, was it Monet that did the amazing sunsets? Yeah, maybe. You can correct me if I'm wrong. And then for a long time, we thought it was artistic license. We thought, well, he's just being sort of overblown and artistic. But actually, if we look, there are big volcanic eruptions at that time, which put a whole bunch of particles into our atmosphere, and so probably did create pretty amazing, spectacular sunsets that were painted at that time. So I think that's really fun as well. So that's me scattering. Okay. So we have transmission, things coming straight through. We have scattering and reflection from different surfaces, from gas molecules, from particles. And lastly, we have absorption. A certain amount is absorbed, okay? And so if we think about sort of plants, for example, what color are plants? Green, okay. So why do we see that green color? It's not because they're absorbing that green. In fact, they're absorbing the blue and the red. And so what we're actually seeing when we see that green is what's reflected back to us, okay? So basically, we see the things that are reflected. We don't see what's absorbed, okay? And so a certain amount of energy is absorbed. So I want you to think logically now. I know this is a challenge on a Thursday afternoon after lunch, but think logically. How much visible light do you think is absorbed by the gases in the atmosphere? Do you think all of it? Do you think most of it? Or do you think very little of the visible light is absorbed by gases in the atmosphere? What do you think? You can consult your neighbor if you want. Okay. Let's see how logical you're thinking. If the gases in our atmosphere are absorbing most of the visible light, would you be able to see me? So thinking logically about it, the gases in our atmosphere can't be absorbing all of the red light or something, otherwise I wouldn't be able to see your t-shirt. Or blue light, otherwise I wouldn't be able to see your t-shirt, okay? And so the atmosphere gases, they don't really care about visible wavelengths. They are not really absorbing it. And we know that because you can see me, okay? So thinking logically. So that's what we see. If we look at our visible wavelengths, for example, we can see that we've lost a certain amount, but most of that is due to that reflection or that scattering, okay? The gases in the atmosphere aren't really absorbing the different wavelengths, okay? But where do we see big gaps? What sort of wavelength ranges are we seeing big gaps where there should otherwise be radiation arriving here? The infrared. So you said, I remember I said before, we were seeing these big gaps all of a sudden that appeared. So there's one here, there's one here, there's one here. And they are associated with particular wavelengths. And this is because the gases in our atmosphere don't really care about visible radiation, but they do care about certain wavelengths of infrared radiation. And that's going to be important later on today as well. So that's what's happening to that radiation as it comes through our atmosphere. So let's think a little bit more now about what's sort of going on. So this is quantitatively what's happening to that energy. We get a certain amount of energy arriving. Maybe 19% of it is reflected by clouds over Earth's surface. Another 6% is scattered back to space by the atmosphere. We maybe get 5% reflection by ground surfaces, okay? And then 25% is absorbed by gases or clouds, and 45% is absorbed by the surface, okay? So if we add up what's absorbed, what percentage is absorbed in total? 70, everyone's mental maths is there, okay? So the word we use for this is albedo. So if we're absorbing 70%, we're reflecting away 30%. And that's what we call our planetary albedo, okay? Basically, albedo is just a word for the fraction of incoming radiation that's reflected away. And it's reflected away, and so it doesn't have any part in heating up the Earth, okay? So our planetary albedo is 30%, or it's sometimes written as 0.3. Either of those is fine, okay? So can you think of any ways, so I want you to think of one short term, one long term, way in which Earth's albedo might change. how might we change the amount of radiation we're reflecting straight back to space? How about on a day-to-day time scale? What do you think we might change on Earth's surface? Yeah? So that's a really important part later. So that's going to be to do with absorption, but we're going to think about reflection. So you're just one step ahead of me, okay? Yeah. Ice melting, absolutely. So not so much here, but at least in the northern parts of the northern hemisphere, we have a huge amount of snow cover. So seasonally, we might see a really big change if we cover a huge area with nice white reflective snow, and then we melt that back, say in the spring. So that would have a really big effect. What might else change even on shorter time scales? Yeah? Cloud cover, absolutely, yeah, day to day. Yesterday was incredibly hot, and we didn't have that much clouds. Today we're seeing a bit more cloud cover, and it feels different, right? And so clouds change really rapidly on Earth, and so that's one way we could change our albedo as well. What about really long time scales? Ice ages, absolutely. If we went back 20,000 years, we would see amazing sort of big ice sheets over a lot of North America and Europe, and that had a huge effect on our albedo. In fact, if we change any old surface on Earth, if we change deserts into forests or into grassland, then we're going to change our albedo. And so my first mean question of the day is, here I've got a table showing you the albedo of lots of different surfaces. So unsurprisingly, fresh snow is something like it reflects back 60 to 90% of the incoming radiation. Water reflects only 5 to 10%. It's really good at absorbing basically anything that hits it. So thinking about that, which of my four things there would act to decrease Earth's albedo and so decrease the amount of energy reflected back to space? So I'm going to give you 2 minutes to think about this. So go through each in turn. Which would decrease? Okay, I think that's more or less everyone. So let's see how we're doing with this. Good work, guys. Well done. I'll take that. So increasing sea level. So increasing snow cover, we're going to increase our nice white area, so we're going to reflect more. That would increase our albedo. Same thing if we increase cloud cover, nice white fluffy clouds are going to reflect more back to space, so that would also increase. So we were left with B or D. So D, if we look at how much or what the albedo of grassland is, it would reflect maybe 18 to 25% of incoming radiation. If we replaced all those grasslands with deserts, which reflect maybe sort of 5 to 30 to 50, yeah, 30 to 50, I can't see from this angle, then we'd actually be reflecting much more of that radiation back to space, okay? And so actually the answer is B, increasing sea level, because water is by far the most absorbing surface. So even if we're flooding sand, if we're flooding grassland, whatever we're flooding, we're going to replace that surface with something that's going to absorb more. So well done, guys. Hopefully that will help with the quiz. So we're reflecting back a certain amount, but that means that we're absorbing 70%. So we're absorbing 70% of that incoming watts per meter squared every single second. So why aren't we heating up and heating up and heating up and boiling off our oceans and vaporizing? Why do you think? What are we doing as the Earth because we have a temperature? Yes? Oh, sorry, yeah, at the back.
We're building more roads.
Sorry?
We're building more roads.
We are definitely building more roads, and that will affect sort of the different surfaces. But what is the Earth doing that might get rid of some of that energy? Yeah, we have a temperature, right? Everything above 0 degrees Kelvin emits radiation. So because we have a temperature, we are also emitting radiation out to space. And what happens is that we emit the same radiation out to space as we get, as we absorb, okay? And so the fourth thing that affects our planetary energy balance isn't something we can really control that much. It's the fact that because Earth has a temperature, we are also emitting radiation, okay? And the key thing is that that is in balance. So whatever we're absorbing, the solar energy absorbed, okay, that 70% that's coming at us, is equal to the energy that we're emitting. And this is very broad. This is over the whole Earth, over, say, a year or something like that, okay? So solar energy absorbed equals terrestrial energy emitted. And that's our planetary energy balance, okay? And do you remember that we have our Stefan-Boltzmann law that says that the amount of energy that we emit is equal to some constant times the temperature to the power 4. So if we know what we're getting from the sun, if we know what we're absorbing, we know what we have to emit, and we can work out our temperature, okay? And you'll have a chance to do this in discussion next week. It gives you a chance to work through some of these questions. So, but what type of energy do we emit? So remember, we also talked about this on Tuesday. I said it was going to be important. If we put into Wien's law rather, the temperature of the sun, which is about 6,000 Kelvin, then what the sun is mainly giving out is that shortwave radiation, those visible wavelengths. If we look at what the Earth is emitting with its average temperature of maybe 300 Kelvin, then we're emitting infrared radiation, we're emitting long-wave radiation. And so that's really important when we talk about our fifth thing, which is our greenhouse effect. So everyone's heard of the greenhouse effect, right? More or less everybody? But no one can really explain it. We know it's a thing, but we don't necessarily know how to explain it. So let's go through what's going on with the greenhouse effect. So this is the diagram that I want you to focus on. The words are there for your notes. I don't want you to be reading the words right now. I want you to listen to me, okay? So this diagram looks horribly complicated, but it isn't, and we'll talk through it just for a couple of minutes. So you can see that I have lots of different gases here. I have methane, I have nitrous oxide, oxygen and ozone, carbon dioxide, water vapor, and then basically this down here is adding up all of these above. And I have wavelength of radiation down at the bottom here, going from shortest at this end, which is my ultraviolet radiation at this corner, to longer at this end, which is my infrared radiation. Okay? So we go from ultraviolet, which is very short, through to visible, which is also short, into infrared, which is what we call our long-wave radiation. And up the side here, wherever you basically see a colored area, is sort of, we're saying that this particular gas, so for example, carbon dioxide, you can see that there's a little peak here in the carbon dioxide graph. It means that it absorbs nearly 100% of radiation at this particular wavelength. Okay? If we go up to, I don't know, methane, you can see that it absorbs nearly 100% of radiation at these particular wavelengths. Okay? Does that start to make sense now? Maybe? Seeing complete nothingness there. Nod or shake? No one's doing anything. Okay, so basically what that shows you is that, let's have a look at my red box. So this is my visible part of the electromagnetic spectrum. And you can see that those gases that I talk about, all of the things like oxygen, methane, nitrous oxide, is there anything that really absorbs the wavelengths in that particular box? Mostly no. There's maybe a tiny, tiny little bit in the oxygen and ozone part. But really, most of those wavelengths don't really get absorbed by gases in the atmosphere. And that's what we said, right? It's logical. I can see you, you can see me. Okay? So that's what's happening. We have that visible light, which is the main sort of type of radiation hitting the Earth from the sun. And it comes straight through the atmosphere, apart from the bit that's reflected. Because the gases that are in the atmosphere don't really care. Okay? It can be transmitted straight down. But what is the Earth giving out? Infrared. And are there any gases that absorb in the infrared part of this? Yes, a lot of those gases. The ones that you've heard of, things like methane, things like carbon dioxide, and others. So I have a quick question for you. Which of those gases on my diagram absorbs the most infrared wavelengths, which is basically the most effective greenhouse gas. So let's see if we get the same answer. Yes, 70% of us do. Water vapor, absolutely. So it's not often talked about, but water vapor, if you look down here, which is basically my blue row here, you can see that water vapor absorbs all of these different wavelengths of radiation. Okay? It's a really very, very effective at absorbing outgoing infrared radiation. Okay? And so definitely things like carbon dioxide are important as well, and methane. But water vapor is there in very large amounts, and it's really good at absorbing a whole bunch of different wavelengths of that infrared energy. Okay? And so what you might notice, though, is that there is little gaps, and in particular there's a little gap around here, okay, which corresponds to that sort of peak radiation that the Earth is giving out. So a certain amount of that infrared radiation given out by the Earth does escape out to space. Okay, a certain amount of it does. But a lot of that infrared radiation given out by the Earth is actually absorbed by gases in the atmosphere. And as that energy is absorbed by those gases get warmer. And those gases then give out infrared energy because they're also warm, they have a temperature. And that energy, some of it goes out to space, but some of it also comes back down to Earth. And that keeps us hotter than we otherwise would be. Okay, if we didn't have our atmosphere, solar energy in, we'd just emit energy out to space. But because we have this atmosphere, we have these gases which trap that energy as it's trying to go out to space. And it keeps it down here where we are, and so it keeps us much warmer than we'd otherwise be. We're basically recycling some of that energy. Okay. And so that's sort of what explains our little dips here in the infrared spectrum. That's what we're absorbing. Okay. And I talked about all of the gases except one, which is ozone. If you look along the oxygen and ozone, what range of wavelengths is that ozone mostly absorbing? Ultraviolet, UV. This is why our ozone is so good. It's absorbing nearly 100% of that ultraviolet radiation instead. And so that's why it's different. Ozone has nothing to do with climate change. It's its own different little problem. Okay. So this is what we have in terms of the greenhouse effect. And it's basically the same thing. Who's ever been in a greenhouse? Okay, quite a lot of people. Good, more than I might have thought. And so the idea is that if you stand in a greenhouse, the reason that we use them is that it's warmer on the inside. Especially in England, you need them quite a lot. And that's because the sun's energy, that visible wavelengths, can come straight through the windows. That energy is absorbed by all of those different surfaces. And then that energy is then re-emitted out. But it's re-emitted as that long-wave radiation instead. And that long-wave radiation can't get through the windows. It's absorbed by the windows, and then those windows emit some energy out, but also they emit energy back in as well. And so it keeps the greenhouse much warmer than it would otherwise be. Is the greenhouse effect a bad thing? So everyone's had a class with me before, so sometimes is a bad thing, but mainly it's a pretty good thing. Because if we didn't have any greenhouse effect on Earth, we basically wouldn't be here. Because the average temperature on Earth would be about minus 18 degrees Celsius, which is really, 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 really cold. It's pretty miserable. You won't have much agriculture, even at the equator, that sort of temperature. So 0 degrees Fahrenheit. Has anyone ever experienced 0 degrees Fahrenheit? 1, 2, 3, 4, a few. It's cold, right? Yes. With our greenhouse effect, we actually have a much more comfortable, reasonable temperature. We have something like plus 15 degrees Celsius, not for you in Southern California, I know, because you like it warm, but 60 degrees Fahrenheit. It's pretty reasonable average temperature for the Earth, okay? And this is the same reason, I should say before I move on, the greenhouse effect is not the same as global warming, climate change, whatever else, okay? The greenhouse effect is necessary for life to exist on Earth. The extra amount of greenhouse effect, the extra CO2 that we're putting in, that is anthropogenic climate change, that is global warming. The greenhouse effect in general is something that's important to keep the Earth. It's that extra bit, okay, that is what is concerning us. Is that distinction clear? Okay. So a more familiar analogy for you is this is why your car heats up on a hot day. Maybe a third of the class have been in a greenhouse, but everyone's been in a car, and everyone knows how miserable it is to get into a car on a really hot day, and you always try and park in the shade and fight people for that spot. Because that visible radiation is coming through your windscreen, through your windows. It's being absorbed by your lovely black seats or whatever else, and then it's being re-emitted as infrared, and it's not making it through those windows. Okay, so this is why your car heats up. So why do you see this around campus? Why is this a good idea? Why does this stop your car heating up? So think about what's happening by... So let's take a look. That's better. I'll take that. Okay, so it's changed a little bit at least. So it is, in fact, the reflection of shortwave radiation. So what you're doing is basically bouncing back what's coming in, right? So we have this visible radiation coming from the sun, coming through the atmosphere, and it would come through your windows. And once it's absorbed by your sort of car surfaces, then it's being emitted as infrared. So we want to stop that process before it happens. And so if you imagine what we want to do is try and reflect back that visible radiation, because if we reflect it back and it's still visible, it will go out through the car. If it's being absorbed by any surface, then it won't go back out through the windows because it's infrared. Does that make sense now? Have a think about it, maybe if not? Okay. So this is a nice little summary of what's happening, okay? And so it's basically describing all of those processes that we talked about. Our energy is coming in from the sun. We have 30% of it either from the ground or clouds being reflected back. That's our albedo, that 30%. 70% is being absorbed, okay? We have a certain amount of energy moving around in the atmosphere because the gas itself moves. But don't worry too much about that. So you can ignore that one if you like. But we also have a certain amount of infrared radiation being given out by the Earth because it has a temperature, because it's absorbing energy from the sun. That energy is then being absorbed by gases in the atmosphere. Some of it might escape through, but a lot of it is absorbed. Some of that energy that's absorbed by the atmosphere is then radiated out by the atmosphere. Some of it goes out to space, and some of it comes back down to Earth. Okay? And so if you look, what's coming in, 100, 30 is reflected back, 70 is going out. So what's coming in is equal to what's going out. But you can see that because we have this extra amount coming back down again, the Earth's surface is warmer. We're basically recycling energy in this part of the Earth system. Okay, that's our greenhouse effect. And that's our planetary energy balance. So if we look at the top of the atmosphere, what's coming in is what's equal to what's going out. But down here, because we have an atmosphere, we have this greenhouse effect, and it keeps us warmer than those numbers might predict. And you'll have a chance to do that in discussion. So those are our 5 factors that affect our planetary energy balance, that control our global temperature: solar luminosity, distance from the sun, the atmosphere and our albedo, the fact that Earth has a temperature and radiates energy, and the greenhouse effect, the fact that we have certain gases that absorb that outgoing energy and trap it near Earth's surface. Okay? That's our planetary energy balance. So those are the factors. So now let's have some fun with it. Now let's actually think about how those have changed through time. How might they be different on different planets? And think about what we can learn. So first of all, remember I said that Earth is a Goldilocks planet, both in terms of being in space, but also through time. We've had this increase in solar luminosity and brightness, right? And if we had the same atmosphere we had today in the past, if it was 30% dimmer, it should be 30% sort of, or we should be a lot cooler in the past. But we don't see that, okay? And we don't see that, why? What was the composition of our atmosphere actually like earlier on in Earth's history? What made up most of our atmosphere? CO2 and sulfur dioxide, water vapor. Where were they coming from? Volcanoes, absolutely. And so you can see there's a number of things going on in this diagram, but it's basically representing the Earth through time. So we have lots of volcanic activity very, very early in Earth's history, okay, and that created our atmosphere. And you can see this top line shows the solar brightness through time with our sun getting more and more luminous. Here in this line you can see what is happening to our surface temperature. If anything, we've actually been cooling down a little bit. And so why has that happened? What's been counteracting this increasing brightness? And it's because at the same time that the sun has been getting brighter, we've been losing carbon dioxide, the steady amount from our atmosphere, okay? And you can see that, again, atmospheric oxygen starts increasing maybe 2 billion sort of to 500 million years ago. And so there's this amazing idea that on Earth, at least, there's been this perfect correlation of our atmosphere changing at the same time that solar luminosity has been increasing, that has allowed our temperature to stay just in that right range for liquid water to exist, for life to exist. And that's absolutely amazing. And there's really fun, interesting ideas about how much of a role does life itself play in that. If we hadn't had the evolution of life, we wouldn't necessarily have been removing CO2 from the atmosphere so much. Does life itself play a part in controlling planetary temperature? If it gets too cold, do we have less life, therefore CO2 can build up? Things like that. It's this really interesting idea. It's called the Gaia hypothesis, if anyone's interested in that. But there's a couple of exceptions, and they're really fun exceptions. So an exception is called the Snowball Earth. It's one of my favorite times in Earth's history. And a couple of times, around 700 million years ago, so before the time when life got sort of really going in terms of multicellular life, there was evidence that we could find in the geological record that glaciers had made it almost all the way to the equator. And we thought, this must be rubbish, that can't possibly happen. And then we found out about plate tectonics, and then we thought, oh, well, it's the continents that must have moved around, and that's why we see this evidence. But as we've reconstructed where the continents were through time, we found that actually, we're back to our first idea, that these glaciers must have reached almost to the equator. And so there's this idea, which we call the Snowball Earth hypothesis, which is really a fun name, I think, that says is that basically the Earth nearly completely froze over. There were maybe a few little open patches of ocean or a couple of open patches of land near the equator, but we were really almost completely frozen solid. And this was obviously not good for life. It's probably a very, very challenging time for that. So how did this happen? And once it did happen, how on earth did we get out of this? How did we get to this much nicer environment which we are today? And it's to do with albedo. So we're going to do a very simple little feedback loop, which a lot of people in my classes have seen before. And so we're going to use a specific type of terminology, but it's really very basic. It's very logical, so don't panic. What we're going to do is draw arrows between these boxes to represent changes that happen in the Earth system. And when we have an increase leading to an increase, so if we increase temperature, we increase something else, we're going to draw that sort of normal shape arrow. If we have an increase leading to a decrease, or a decrease leading to an increase, we're going to draw this other type of arrow. Okay? So I'm going to talk you through this first example. So my example, we're first of all going to cool down the temperature of our planet for a little bit. For a number of different reasons we could do that, so I'm just going to start off by cooling it down a little bit. If I cool down the temperature of my planet, what am I going to do to the amount of ice on Earth? I'm going to increase it, right? So what type of arrow am I going to draw between those two? Am I going to draw a normal one, or am I going to draw like an arrow with a circle at the end? For a decrease leading to an increase, I'm going to draw the arrow with a little circle at the end. Okay? So when there's a change in the direction of that arrow. Okay? So I'm going to draw my connection like this. If I'm changing the amount of ice on Earth, I'm going to change the albedo. I'm changing the albedo, I'm going to change temperature again. So we've got a little feedback loop going on. Okay? So I'm going to give you 2 minutes or so, because I'm confident that you can do this, and the TAs will wander around as well. See if you can complete this loop For those of you that have done this before, it's nice revision. It's nice review. Okay, well the people I talk to have got this, so I obviously don't have to spend too much time after all. So if I'm increasing the amount of ice on Earth, what am I going to do to my albedo? Increase. So what type of arrow am I drawing? A normal one or one with a circle? Normal, absolutely. So I'm increasing that, so I draw my normal arrow. If I'm increasing albedo, what am I doing to the temperature? Decrease, thank you. I had a bit of a mixture there. So if I'm increasing albedo, I'm increasing the amount reflected, so decreasing the amount absorbed. And so the temperature is going to decrease, okay? And so what sort of arrow would I have there? The one with the circle, okay? So it's a very simple idea, and this is sort of what we use to draw out feedback loops. So you can see that internal to the climate system, if we change one thing, then often that sort of results in a further change. And this is what we call a positive feedback loop. It's an amplifying feedback loop. It's not a positive thing at all, right? It's not a good thing, but it's what we call a positive feedback loop. And in particular, this particular feedback loop led to the development of our Snowball Earth, because we saw a little bit of a decrease in temperature, which led to a further decrease in temperature, which led to a further decrease in temperature, and with this spiral of death, basically, spiral of doom. And so my question to you is, how did we get out of this spiral of doom? What could we do? So someone had a good suggestion for me back here. What did you suggest that we do? Increase CO2. We know that that's causing problems today, right, with increasing temperatures. If we want to get warmer again, we want to find a way of getting warmer. One of the easiest ways of doing that is increasing the greenhouse effect. So how can we do that? We can increase CO2. What could cause there to be more CO2 in the atmosphere? Volcanoes. Volcanoes don't care if we're covered by ice and snow or not. They're still going to continue to erupt, okay? And so over time, I mean, the Earth was like this for a very long time, because what had to happen was we had to have enough volcanoes erupting that we hit this critical point where finally we had enough of a greenhouse effect that we started melting away. So when we started melting away, I increased my temperature of my planet. What would that do to the amount of ice? Decrease. What would that do to the albedo? What would that do to the temperature? So we do the spiral the other way. Basically, we get warmer and warmer and warmer. And so we see this really interesting period in Earth's history where we go from being really cold to really warm. And there's a really interesting sort of theories about whether that sort of extreme swings either way might have been a bit of an evolutionary push for life to become more complicated. So it's an interesting idea. Okay. So absolutely, volcanic activity would raise CO2, increasing the greenhouse effect, and would increase temperature again. So in that case, let's move on to my last little activity. So everyone has their bit of paper, right? No? Okay, who's been taking more than one? So remember, I asked them to share out, so TAs, could you wander around and help pass back some of the bits of paper? So please share. Okay, work together in groups. So let me explain what I would like you to do. So what I would like you to do is take a look at your little diagram there, okay? And what you've got on there is a little line, okay? So what we're going to do is think about where Mars, Venus, and Earth's temperature would be today, okay? And I have 3 challenges for you. The first one is pretty simple. So I have lots of information on the board up there. I have the distance that that planet is from the sun. I have the albedo of that planet. Instead of percent, it's in 0.8, but you get the idea. And then I have the atmospheric composition, so the main gases that make up that atmosphere. And I also have the pressure. And the pressure is basically how much gas is in these different places. So for example, on Earth, we use sort of atmosphere as a measure of pressure, and we have 1 atmosphere of pressure. If we went to Venus, a lot of the gases on Venus are still in the atmosphere. They haven't been removed by processes like they have been on Earth. And so the pressure on Mars is 90 times what it would be here right now. There's 90 atmospheres. There's much more gas in Venus's atmosphere. If we look at poor little Mars in comparison, it's only got 0.007 of an atmosphere left. Because remember, it lost its magnetic field. It's been losing gas out to space. Okay? So the first thing, on your bit of paper, if you look, I've drawn a line. Okay? And so on that line is sort of where the temperature of the planet would be if that was the only thing that affected it. If it was only distance that affected where that planet would be, then that's where it would be. So I'm going to see if I can switch this on. Okay. And we're going to switch to the document camera. So, for example, Venus was, or Earth today, is about 150 million kilometers from the sun. Okay? And so if distance was the only thing affecting temperature, if basically the amount of energy that we got from the sun, then the distance would mean that here's 150 million kilometers where Earth would be, and here, can you see that? Yeah. Here is where Earth's temperature would be if it was only distance affecting it. Okay? So when I put the slide back, you can plot Venus, which is more or less 100. You can plot Mars, which is 200 and something. Okay? Then I want you to think about, well, what happens if we take into account Earth's albedo? Would our temperature, if we just took into account distance and albedo, where would Earth's temperature be? Would it be above this line or below this line? Below would be reflecting a certain amount. So for each planet, think about how far below that line that temperature would actually be given those different albedos. And then I want you to think, well, what happens then if we add back in the greenhouse effect? So then you want to think about, well, how much gas is there? And what are those gases? Okay, and think about the approximate size of the greenhouse effect. How big a greenhouse effect, how small of a greenhouse effect do you think exists? Okay, so I'll give you a good 5 minutes or so for this, and the TAs will wander around again. Okay, and I'll put back up the information. So hopefully you have Venus plots pretty close to there, so I'm going to label that Venus so we don't get confused. Here's going to be my Earth. And here is going to be Mars down here, okay? So what is the albedo going to do? You said it's going to plot underneath the line. Is any one of those planets going to plot further underneath the line than any of the others? Venus. Why Venus? Yeah, its albedo is 80%. It's losing 80% of the energy that's arriving, okay? So if we were to think, I mean, it doesn't matter too much about the absolutes, but if we were to think about what would happen, it's losing 80% of the energy, so it might plot somewhere down here or something. Okay? The Earth is losing like 30%. Okay? So is it going to plot the same distance below? Or is it going to plot closer to the line? Closer to the line, right? In fact, I told you what Earth's temperature was without the greenhouse effect. Does anyone remember? 0 Fahrenheit, but we're working in Celsius, so -18, well done. Someone's very on the ball. Okay, so it would plot somewhere there-ish. Okay, what was Mars's albedo? Do you remember? 0.2, 20%. So is it going to plot closer to the line or further away from the line than Earth? Closer. It's going to be really very close. Okay, it might be down there somewhere. Okay, so everyone's with me now? So let's go back. So now think about what the greenhouse effect would be, okay? So think about what type of gas is in the atmosphere. You already know what the greenhouse effect amount is on Earth, right? Because I gave you that number earlier. You can plot the average temperature on Earth. So then think about how big is that effect going to be on Venus? And how big is that effect going to be on Mars, okay? So what do you think?
Well, Venus is going to be greater because its atmosphere is mostly composed of CO2.
Yeah, and how much atmosphere does it have?
A lot.
It has 90 times the amount of atmosphere and 90% of it rather than 0.0035. So how big is that greenhouse going to be?
Big.
going to be really big, right? It's probably a reason that I put the scale on there that I did. So what about on Mars? Is there going to be much of a greenhouse effect on Mars?
Not as much.
No, not as much at all.
Atmosphere's very tiny.
Exactly. So it's mainly composed of CO2, but it doesn't have much atmosphere. Great. So what do you guys think over here? Where is my biggest greenhouse effect going to be? Easy question. Venus, right? So how big is my greenhouse effect on Venus going to be? Is it going to be just a bit bigger than Earth, or is it going to be a lot bigger than Earth? A lot bigger than Earth, because not only do we have 90% CO2 in the atmosphere rather than 0.035, but we have 90 times the amount of gas as well. Okay, so it's going to be really big. What about Mars? Not so big. Okay. So does someone want to give me their estimate for what the greenhouse effect might be? So if you had to guess, I know you shouldn't really guess because it's not very scientific, but what do you reckon the surface temperature of Venus might be? Okay, so here's our distances, here's our albedos. What do you think the temperature of Venus might be? Hot. Someone want to give me a number? 200? 450 is pretty close, pretty close. So Earth is nice and close, it's about 15, right? How much of a greenhouse effect do you think there's going to be on Mars? More or less than on Earth? Less. It's difficult to say, right, because its atmosphere, again, is mostly CO2, but we have so little atmosphere that it's not going to have a significant effect. So you are, in fact, absolutely right. So Earth plots close to there. Mars, you can see it actually plots underneath. That albedo effect is greater than its greenhouse effect. Venus, apart from the fact that you'd be crushed instantly if you tried to step on the surface of Venus, it's extremely hot. Okay, it's extremely hot. And so those are the average temperatures of Venus. Okay, great. I will see you on Tuesday.